I have posted announcement on Sakai regarding midterm exam and lab report or lab this Thursday. So do you guys have any questions on that? Okay.
So you just need us to operate the SEM and just take some pictures real quick for that?
Yeah, basically, yeah. So I mean, so I already prepared some nano materials, okay, and then I placed those on TM grid. So like it's already prepared. So you guys are gonna come and basically look at kind of how those nanoparticles or carbon nanotubes look, okay, and based on that, you guys will you guys expect to write a short lab report, okay. Yeah. So I think 15 minutes might be enough, or like actually you might need more time because these nanoparticles and nanotubes are quite small, right? I mean, if you look at the actual lab manual, diameter is about 10 nanometers, and like the nanotubes or nanoparticles are about like 40 nanometers. So you have to actually zoom in quite a bit, and for that one, like I mean, depending on actually the operator, like how to adjust the stimulation, focus, brightness, and contrast, it may take some time. But once you figure that out, it should be straightforward. Okay? So how many of you guys have not used SEM before? Okay, I see. So for those who have not seen, SEM, this might be actually quite interesting, yeah? Because this SEM is actually a very powerful tool, to cover the materials ranging from, even like a large scale, like a millimeter scale or micrometer scale, down to nanometers. Okay, but I mean, yeah. So if you need a really kind of atomic scale resolution, you have to work with a transmission electron microscope or scanning tunneling microscope. Like even for actually nanoscale material characterization, there are actually a variety of characterization tools available. But like I would confidently say that SEM is one of the most popular like tools. Okay, so, and actually here SEM is free. Like to operate it is free. But if you actually kind of go to like civilian university or any other places, the hourly charge is typically about $100. So every time you use, like every hour you have to pay $100. Yeah. So it's actually quite expensive tool and very powerful tool. But here, actually, you can get training on that, and if you become authorized user, you can just use it for free. How many hours? Yeah. So if your research area is on like some nanomaterials or small scale materials, you probably want to look into SEM characterization, because it's fairly easy and then like useful. Okay. All right. Okay. So any other questions? So for the exam, probably sometime next week I'll kind of have some like a quick review. Okay. So yeah, that might be actually useful for you. And in terms of a difficult level, like difficult level, it's gonna be similar to homework. Okay. So, yeah. All right. Okay. So we have been working on this harmonic oscillator, and then today we are going to look at a couple of examples. How this harmonic oscillator is useful for interpreting some other phenomena here. Okay. So first example is, and also we are almost done with this lecture note part. Okay, so probably this week we can wrap up all the lecture note part, and then from next week we'll just kind of use just PowerPoint. Okay, so just want to let you know. Okay, so this is one example of a harmonic oscillator is electromagnetic wave with frequency, specific frequency loop. Okay, so the photon, so is essentially kind of defined as h Okay, Planck constant, and then the frequency here, and then n plus 1/2, and then here n goes from 0, and it can only take integers. Okay, so here n is the number of photons in the field, electromagnetic field having frequency nu. Okay, photon. Yeah, probably like many of you guys have heard about a photon, right? So photon is related to actually electromagnetic wave, and then the simplistic way of kind of defining photon is, basically quantized energy in electromagnetic wave. Okay, and then that one is related to harmonic oscillator. So for example, the photon is basically each photon has energy of h nu. Okay, so that is essentially like a fundamental photon energy, and then number of photon is typically kind of defined by this number of n. Okay, so for example, if you have higher n, what does it mean in terms of photon? It has higher energy, right? So basically like higher energy of a photon. So that one is related to or corresponding to this n. Okay, so higher n indicates basically like how many number of photons, and which gives like the total energy of that electromagnetic wave. Okay, so the way it comes, the way it's defined is essentially kind of starting from black body. Okay, so for example, for any matters, for example, atoms, electrons, okay, so as long as the temperature is higher than absolute 0 Kelvin, okay, this is 0 Kelvin, so then it has a thermal energy, right? And then electron kind of acceleration is observed, right? Because this has an internal kind of thermal energy, it kind of like oscillates. Okay, so that one comes with the electron acceleration, and then that causes or generates electromagnetic wave. Okay, so and then these electromagnetic waves contains obviously spectrum of various EM standing waves. Okay, so think about this kind of black body, like the black body, by definition, how it's kind of described here is you have a very small hole, right? And then once the kind of light comes in, it basically bounces there. It's kind of like completely absorbed, and then it completely kind of emits the electromagnetic wave. Okay, so this is essentially kind of how the black body is described, and in this case, it has a various spectrum, okay, of a standing wave, and in this case, each mode, okay, each mode is essentially considered as quantum harmonic oscillator. Okay, so this is why when you actually look at this photon energy, this one has n plus 1/2 h nu. So this relationship is exactly same as the one we obtained from this classical, or the harmonic oscillator here, right? So this is the energy description by solving Schrödinger equation for the harmonic oscillator here, right? 1/2 kx square. So this is essentially kind of how it's related to electromagnetic wave. Okay, so in a simple way, you can think of this electromagnetic wave as harmonic oscillator. Okay, and so this one, if I kind of also this one. We kind of saw this figure before. for ideal black body at a given temperature, for example, 5,900 Kelvin, it has a various irradiance or emittance, okay, at various wavelengths, okay. So at this particular frequency or wavelength, that one can be thought of as harmonic oscillator, okay. Okay, so this one is also not surprisingly, like this is a consistent with Einstein's explanation for photoelectric effect. So what was his idea? Energy of electromagnetic wave is essentially given as h nu, right? So this is essentially kind of a one photon, but obviously if you consider many photons, you just basically add them up, right? 2h nu, 3h nu. So in the sense, if you actually go back here, this is related to that, right? Here, essentially, like n goes from 0, 1, 2, right, and so on. It keeps going on, right? N can be large number, but one thing you can notice here is that this one is quantized, right? Only multiples of h nu is possible, right? So n cannot be like a 0.0001 or 0.1, 0.2. Nothing is possible. Only energy can go from base is a 1/2 h nu. The next variable is essentially like a 3/2h. Okay, so h nu is essentially kind of added on top. Okay, so in this sense, discontinuous energy. Okay, so this one was for the electromagnetic wave. The second example is atomic vibrations in a crystalline solid. Okay, so like in a crystalline solid, like you can actually model this atomic arrangement with mass and spring. Okay, so I'm gonna just kind of draw just small kind of a subset of a crystalline solid. So in this case, each atom can be modeled as kind of a mass. So in this case, like let me just write down as mass here, and then also there is interatomic bonding, right? Interatomic potential. So that one can be represented by spring constant, like that. Okay. So every mass is connected through the spring. Okay, like that. And in this case, you can think of this atomic vibration in several ways, but specifically if we consider just thermal transport. Okay, if we consider thermal transport, let's say one side is hot, okay, and then another side is cold. What happens is that on the hot side, atomic vibrations are more vigorous. Okay, because it has higher kinetic energy, right? You guys remember, like kinetic energy is associated with actually the temperature, right? Like kind of following kinetic theory. So in the sense, it's kind of vigorously moving here at hot side, and obviously that vibration basically transmit, through the neighboring atoms, and then that actually transfers energy from hot side to cold side. That is how heat conduction actually happens, okay, microscopically. Okay. So you guys learned about conduction, right, in heat transfer, right, Fourier's law. And microscopically, what happens here is, like these atomic vibrations basically transfer energy from hot side to cold side, and then, that is how conduction occurs, okay? And then in these atomic vibrations, like when you think about this, like a vibration through the spring and mass, it can be decomposed into various modes, okay, either into normal mode, okay. So basically, like, all the vibration is a sum of certain frequency contributions, okay. So in the sense, you can actually decompose into specific frequency or normal mode. And in this case, energy of each mode for that crystalline vibration or atomic vibration can be described as, again, h nu. Here is a 4 known n plus 1 half. Okay, n goes from 0 to 1 to, again, the same idea. But have you guys heard about 4 known? Like this is not about photon, but have you guys heard about 4 known? So this 4 known is the quantized energy in atomic vibrations. Okay, so in the sense that this one is actually kind of important concept in heat transfer. Okay, this is not about photon. This is about 4 known, and 4 known represents quantized energy in atomic vibrations. Okay, so basically 4 known here is quantized energy of crystal vibration or crystal lattice vibration. Okay, so again, in this case, because of this spring mass system, you can think of this as kind of a harmonic oscillator, and then that is why this energy of phonon or atomic vibration can be described as harmonic oscillator. Okay, the equation we got. Okay, so these are the kind of examples we can talk about for harmonic oscillator. Okay, and then with that, let me just kind of go to the PowerPoint, and then I want to describe something else. But before we move on, do you guys have any questions here for harmonic oscillator?